guys, in this short video, we're going to be talking about the relationship between Ka and Kb, which are the dissociation constants for a weak acid and a weak base, respectively. So with this particular slide, we're going to be deriving the equation that is showing at the bottom. Alright guys, in this short video we're going to be looking at the relationship between Ka and Kb, which are the equilibrium constants for the dissociation of a weak acid and a weak base respectively. We're going to be deriving specifically the equation down here at the bottom, which is really useful and which you should get to know. But to derive this equation, what we're going to do is that we're going to look at the dissociation of a weak acid, and then we're going to be looking at the behavior of a weak base and finding the expressions for Ka and Kb, and then multiplying them against one another. So to begin with, let's say that we have a particular weak acid HA, where A represents the anion of that acid. We know that that weak acid partially dissociates into hydrogen ion and the respective anion. And we can write the Ka for that process by taking the products and dividing them by the reactants. Separately, we're going to deal with a base. So this right here is representing my weak base. I could have also written it as B, as we had done in a previous video. But remember that for the base, you always need to react it with water because there has to be a source of protons. That base is going to do what bases do, which is to accept a proton. And so on the other side, what I have is the conjugate acid of that base. In this particular case, that would be called HA, right? And then my other product is the remainder or the conjugate base of water, which is going to be the hydroxide ion. I can then write my Kb expression, which is going to be the concentrations of my products divided by the concentrations of the reactants. And of course, we have to remember that water, in this particular case, it's a pure liquid and thereby it's not going to participate in the equilibrium. If I then take Ka and multiply it by Kb, that would be basically this term from Ka and this term from Kb. And if you notice, there's a couple of things that we can cancel away. For example, the anion cancels away. Similarly, the acid concentration cancels away. And so what we're left with is that Ka times Kb is equal to the hydrogen ion concentration times the hydroxide ion concentration. And if you recall, we previously said that that right there is defined as your Kw. Therefore, we arrive at the equation here at the bottom that says that Ka times Kb is equal to Kw, where Kw, you might recall, is 1 times 10 to the minus 14 if we are talking about a temperature of 25 degrees Celsius. Now, in tables and online, you will usually find either the Ka or the Kb for the substances that you're interested in. So this equation is really useful because it allows you to calculate one from the other. For example, if I wanted to calculate Ka, I would say Ka would be equal to my Kw divided by Kb, or similarly, if I was looking for Kb, Kb would be found by taking Kw divided by Ka. All right, let's go ahead and do an example. So the question is, calculate the base dissociation constant for the nitrite ion. And so what we're going to look is at the table that we have available with information. You might see that we have a list of weak acids together with the value of their Ka. Of course, nitrite is not an acid, so what we're going to look for is the conjugate acid of this base. This is actually a base. The conjugate acid of that is going to be obviously HNO2, which is nitrous acid. And here it is, nitrous acid. Here we go. The Ka for nitrous acid is provided, but in this particular case, we're being asked for the base dissociation constant. Therefore, we're going to have to solve for the base dissociation constant using the equation in the previous slide. We had that Kw was equal to Ka times Kb Therefore, our Kb will be equal to Kw divided by Ka. Kw at 25 degrees Celsius is 1.0 times 10 to the minus 14. And if we divide it by the Ka here, which is 4.5 times 10 to the minus 4, we arrive at the conclusion that Kb is equal to 2.2 times 10 to the minus 11. And that right there is our answer. Now let's look at a little bit more complicated problem. Calculate the base dissociation constant for the phosphate ion. And what we have is a list of weak acids together with the value of their Kas. All of these acids right here are actually polyprotic acids, so they have more than one Ka. Each of the Kas is representative of one dissociation, either the first dissociation, the second dissociation, or the third dissociation, if the acid happens to have 2 or 3 acidic hydrogens. In this particular case, of course, we know that the phosphate ion comes from the acid phosphoric acid, H3PO4. So we're going to look for that in the table, and here it is, phosphoric acid, H3PO4. Notice that that one has three Kas, and so which one are we going to use to find the base dissociation constant for phosphate? The way that I think about it is I start thinking, okay, the first dissociation of taking H3PO4 and dissociating it is going to generate H plus H2PO4 with a -1 charge. That's my first dissociation, and that one is associated with Ka1. This guy right here is not what I need yet, so I need to think about the second and maybe even the third dissociation. So what I'm going to do is that I'm going to take that product, H2PO4 minus, and I'm going to dissociate it once more. This case, that's going to generate H plus what's left, which is HPO4, and in this case with a 2 negative charge. That process is associated with Ka2, the second dissociation. But yet, this is still not what I need. So what I'm going to do is that I'm going to take this guy and I'm going to dissociate it once more, HPO4 2 minus, yes, all is good. And then that's going to give us H plus, hydrogen ion, plus what's left, which is going to be the phosphate ion, PO4 with a 3 minus charge. And that process is associated with Ka3, the third dissociation of the acid. Now, in this particular case, we're being asked for the base dissociation constant of this guy, which means that we need to look at this as if it was acting like a base. When it acts as a base, it accepts a proton and it forms HPO4 2 minus. So really what we're looking at is this third process, but in the reverse direction. Again, we're going to be looking at phosphate acting as a base. When it acts as a base, it accepts a proton to form HPO4 2 minus. And therefore, what I need to do is that I need to use this Ka3 to be able to find the Kb. How do we find the Kb? Well, we're going to use the Kw equation. In this particular case, Kb will be equal to Kw divided by Ka3, which means that we're going to take 1.0 times 10 to the minus 14 divided by Ka3, which is, according to the table, here we go, 4.2 times 10 to the minus 13. And that gives us the Kb as being equal to 2.4 times 10 to the minus 2. And we are done. All right, clicker question for you guys. What is the base dissociation constant for the ion Cn minus or cyanide? So what would you do in this case? Of course, you need a little bit more information. You should actually go back 2 slides to the table and look for the Ka of the hydrocyanic acid. So if we go back, not to this table because this one has polyprotic acids, but the table before that, in here we're going to be able to find hydrocyanic acid right here. And notice that the value is 4.9 times 10 to the minus 10. So I'm going to come back here and say, okay, so I know that the conjugate acid of this is HCN, and I know that the Ka for that hydrocyanic acid is 4.9 times 10 to the minus 10 according to the table. What I am being asked for is the base dissociation constant for it, so that means that I'm going to be solving for Kb, which is going to be equal to Kw divided by Ka, and that's equal to 1.0 times 10 to the minus 14 divided by 4.9 times 10 to the negative 10. That gives us a Kb, which is equal to 2.0 times 10 to the minus 5. So your answer was number 3. All right, guys, that is it for this video. See you on the next part where we learn about the pH of salt solutions.